So, hello and welcome. Happy to see a couple of faces that are still here after a long day, but I promise I will keep it on the short side, this talk, so there will be plenty of time afterwards. If you have some questions, you can just ask them directly in this round or come to me, whatever you prefer. I will talk about QUARK today, the application-oriented benchmarking tool for your quantum pipelines. And some of you might have already heard of it, many might have not. For those who did not yet heard of it, I hope this next 12 to 15 minutes will give you a nice overview of what we at the BMW Group think of benchmarking in general and what role QUARK plays in it. And for those who already do know QUARK, there will also be a couple of slides about the latest version of QUARK, which just came out a couple of weeks ago, so there will be something new for you as well. First, I want to start with what we actually mean when we say benchmarking and why we think it is relevant. In this room, and probably in the other one as well, there were plenty of mentionings of benchmarking already, I imagine. But when we talk about benchmarking, or when I talk about benchmarking in the next couple of slides, I talk about application-oriented benchmarks, which is different from circuit layer benchmarks, hardware-oriented benchmarks, which are super relevant in their own right, but I'm talking about the evaluation of the performance of quantum computers compared to classical methods and hardware in industry-relevant use cases, right? This is basically what I mean by this term. And why do we think this is important? The basic idea is that we think it is relevant to have a strong community between academia on the one side and industry on the other. Because the industry needs to understand what's actually possible with today's hardware, with future technology, in terms of qubit counts, error correction code, and so on. And the academia needs to understand what the actual pain points of the industry are, because only then can we have a guided development towards a future where quantum is actually useful, and we have a quantum advantage hopefully in the next couple of years. Now, when we came up with QUARK a couple of years ago, we designed it as a modular framework, which means that it should be as easy as possible for everyone who wants to use it or who wants to contribute to add their own customizable modules so that they can build their own pipelines for whatever benchmarks they want to run. But these pipelines need to be transparent, and the metrics and parameters that they use will be public to everyone because QUARK is an open source project. This is done by using standardized data types that are used between these modules so that the pipelines that you come up with at the end can be reproduced by everyone who tries that themselves. Benchmarking is not only relevant for us in the industry and in academia, as I said, but it's also a very prioritized topic on the government levels. This is true for the government level of the European Union, on national level, regional, and even local level. This is just a short list of official publications done in the last couple of years, where standardization and benchmarking are in the focus of quantum computing become mature in the next couple of years until the end of the decade. The BMW Group is part of funded projects that are partially funded by these institutions, and thereby drives this point forward with QUARK in its center. And this short history and evolution of QUARK shows you that it really fills this need for a tool for this standardized application-oriented benchmarking that I'm talking about. As I said, we came up with the idea of QUARK like 4 years ago as an internal tool just for basically automatizing our own workflows, so we don't need to rewrite code every time we run a quantum benchmark. And then we thought it would be a great contribution to the quantum ecosystem to make that publicly available as an open source project, which we did in early 2022. back then with only 3 optimization use cases, which then in the years after that grew into a proper framework with quantum machine learning use cases, which became part in QUARK 2.0 in late 2023, and the steep growth of external contributors as well, with a peak in the numbers of applications and contributors in July of this year, when we realized that in order to give QUARK the chance to further scale, we need to make a next step towards the latest version of the framework, which is QUARK 3.0, which I will come to in a couple of minutes once more. Throughout this history that I just showed, QUARK was always driven by a strong community of developers inside BMW, but even more importantly, outside of BMW. This helped us to have frequent releases since 2022, when it was first published, with new problem kernels, now also in the domains of quantum machine learning and simulation, as I showed before, with new features, new quantum algorithms, all done by the strong community that grew over the years, now with more than 15 actively participating members of our community that added at least one module themselves. And we also had 3 academic publications in this time span, which were cited over 90 times and counting. Now a couple of words about QUARK 3.0. How is that different to its former versions? As I said, one key aspect of it is that it's way better in its scaling probabilities or scaling features, and this is done by it being very slim and lightweight, which means that the number of packages that you need to install is just like a quarter or so of the number of packages you needed to install earlier, which makes it quick to install and also allows users and developers to add their own modules easier than ever before. It's a command line based interface as always, so if you used QUARK 2 years ago, it still looks the same. You still need to bring your own token, and the data that you use should be publicly available as well in order for everyone to reproduce the results. Now, to give you a concrete example of how that looks like. As I said, QUARK is built out of modules which are connected by standardized interfaces. A typical QUARK workflow includes a pre-process and a post-process, where in the pre-process, your combinatorial optimization problem might be formulated, or your training models might be formulated, the circuits might be built, and then eventually you will bring whatever you want to run on the quantum hardware at the end of the pre-process. Then in the post-process, the result of the quantum hardware you're running your circuits on is then interpreted such that at the end of the post-process you get the results that you're looking for and the solution to your problems. To visualize it even further, I brought the well-known traveling salesperson problem, where you formulate your problem as a graph, you map that graph to a quadratic unconstrained binary optimization problem suitable for quantum annealers, such as the D-wave advantage, on which you then run the problem. When the D-wave advantage is done, you'll get a solution string out of it, which you then retranslate to the solution to your original graph problem. This is obviously just a very straightforward problem, but this is basically all you need to understand about the QUARK framework right now, because each and every module that you come up with in QUARK 3.0 will basically only consist of a pre-process function and a post-process function. The important part is that the data that you provide, the next submodule in your workflow pipeline, is of a standardized data type that the QUARK core framework provides. But in theory, you could add like many more modules, like, as I said, the training modules in between, circuit modules. There will be a larger example about what the BMW group did with QUARK tomorrow in a talk with Nico Kraus. So if you want to learn more about that, then feel free to jump into that talk tomorrow. Now, what are the next steps that we have in mind for QUARK? What is holding in the future? The immediate next steps we have in mind is to make QUARK an application interface to the Munich Quantum software stack and the Munich Quantum Valley, in which we work together with the Fraunhofer IKS, the Leibniz Rechenzentrum, and also the Technical University Munich, where we are currently right now working on the implementation of the Munich Quantum software stack and QUARK, such that we can access the quantum hardware in the Leibniz Rechenzentrum directly. The goal of this is to obviously scale QUARK even further and to make it an even more integral part of the national and beyond quantum ecosystem. Now I want to invite you to become a part of our growing community, be it as a part of our GitHub community with the tag QUARK Framework, in our regular open calls, or the Slack channel in which we update the community with the newest developments on a regular basis. Or you can check out the 3 papers I mentioned on the archive. The QR code that you see here points you directly to the GitHub repo. And with that, I want to thank you once more for your attention and are happy to answer a couple of questions.